So now we're going to talk about the least squared regression line. So if you see here, this is part of a scatter plot. And just imagine that my x-axis is my third exam scores, and it's my independent variable. And my final exam scores are my dependent variable. So say like I wanted to know, okay, traditionally in statistics, the third exam for you is usually your toughest. So I want to know, based on all that tough material, could I predict how well somebody's going to do the final exam score? So maybe I can do, maybe next semester I can put stuff in place that, like, if you didn't do well on the third exam, I can put more in place that you would do well on the final exam and try to break that prediction. So looking at these dots, you could kind of see where I could maybe put a line that would include most of the dots, or maybe not. And you know what? My version of the line could be different of your version of the line. So what we do is we want to create something called the least squared regression line to get the best fit. So we use something called the y hat, and it's an estimate of y. So what I'm going to do is I'm going to make a line, or the calculations are going to make a line, and I'm going to put it between the dots to try to hit as many as I can. But what happens is some of these dots are far away from the line. So as you see here, here's the point on the line, but here's the actual data value. And what they're trying to do is get the distance between here. This distance, when I take that, is called the error or the residual. It's not an error in the sense of, oh, I did something wrong. In statistics, we talk about the error of what we're not accounting for. So the absolute value of a residual measures the vertical distance between the actual value of y and the estimated value of y. That is exactly what that is right there, is the distance between my predicted and my actual. So in other words, again, it's the vertical distance between the actual data value and what I'm predicting. So if the observed data value lies above the line, the residual is positive, and it's underestimating the actual data value. If the data value lies below the line, the residual is negative, and the line is overestimating the actual value. Just know that if you go on and you look at residuals, larger residuals can be negative other than positive numbers. If I had a residual, say, of -5 and a residual of 4, that -5 is going to be bigger because it's a bigger number. So think of it on a number line away from 0, where 0 is the line of best fit, and you're measuring away from that. So it's called the sum of squares errors, and you're never, ever going to have to do this by hand. So basically what we do is we go out and we get all of these errors that are made, and we add them together, and then we take them, we square them, and then we add them together. And you use calculus to get this, and guess what? We don't even have to worry about the calculus. So the computer, the calculator gives it for you. But the thing that's the best part of this for you is you get that line of best fit. The process of getting this line of best fit is called linear regression. And sometimes you're going to hear it called a regression line, a line of best fit, a least squares regression. Many people call it different things. So just be comfortable when you hear it different ways. So the idea of finding this line of best fit is I'm going to be able to make the best assumptions that I can while I try to minimize those errors. And when you do multiple regression, sometimes you'll start taking out certain variables that don't give you good lines. Like if I was going to do income and I wanted to do like years you've been in the industry, the number of years you were in school, I wouldn't put your shoe size in there. But if there was a model that had your shoe size, it might not help. It might actually hinder what I'm doing. So I could take that out and it would probably give me a better line.